Welcome back, Mr. Wakefield here, looking at 4.3 now, and looking at something we haven't seen before in this class, absolute values. All right, but not just absolute value. You've probably seen absolute values before. If somebody says, for example, to take the absolute value of -6, you know that that means to take the negative and make it positive. If they tell you to take the absolute value of a number that already is positive, then it stays positive. In other words, absolute value takes a number and it makes it positive if it's not already. But either way, it's going to end up being positive. Okay, absolute value can never be negative. And that's a good thing to remember, as you'll see coming up here. So what are we going to do with it here in this section, though? Well, we're going to be looking at, let's take a look at the problems down here. We got some equations, meaning that we have the equal signs, and we have to solve those equations. You can see that they look very similar to the equations we've seen in the past. In fact, if you turn these absolute value bars into a parenthesis, a rounded parenthesis, it would probably look quite a bit like a lot of the equations that we've seen. But I want to warn you about that, since they do look so similar. You do not do those same steps. If you see the absolute value bars with a variable on the inside of them, which all of these will have, you do not use the rules that we've seen in the past sections in this class to do these problems that have the absolute value bars in it until after you get rid of the bars. Once you get rid of the bars, then it will truly be an equation similar to one you've seen before in this class. Okay, but do not even think about doing the steps that we learn to solve equations and also inequalities, which we'll see on the back. Don't even think about doing those steps until you get rid of the bars. So the question is, how do you make these bars disappear, these absolute value bars? Well, the first thing you got to do, you can see here that we have 4 rules up here, and it all depends on what the equation or inequality looks like. If it looks like this, and we'll go over that carefully, then the next step is to write this right here, and notice the bars aren't there anymore. Same thing here. If it looks like this, then next step, notice the bars aren't there anymore. Same thing here and here. The bars are here, and then the next step they're not. Okay, but I want you to notice something about all 4 of these things right here. Okay, the bars are isolated on one side of the equation or inequality on all 4 of these rules here. So it is absolutely extremely important, because I see a lot of students completely go in the wrong direction with the problem, and they lose a lot of points that way if they try to solve the problem using the normal methods we've done in the past without actually getting these bars by itself. See, here's the thing. You got to get the bars by themselves before you can use one of these 4 rules. And it's these 4 rules that lead to these results over here, which, because of the fact that the bars are now gone in these results over here, that's what allows you to then use the rules that we've had in the past. Remember, you can't use the rules we had in the past if the bars are still there. So, basically 3 things that we're going to do. Number 1, if it's not done already, we're going to get the bars by themselves. You can see in problems 1 and 2, the bars are already by themselves on one side of the equal sign. Whereas in problems 3 and 4, and I'm sorry, C, D, and E, I'm thinking numbers here. C, D, and E, the bars are not by themselves. Okay, so in C, D, and E, we're going to have to get them by themselves. Either way, you need them to get them by themselves, the bars, on one side of the equal sign. Then you apply the appropriate rule. I'll show you that carefully, don't worry. But applying the appropriate rule will then allow you to make it look like one of these. And then once it looks like one of these, because the bars are gone, then you can solve the remainder of the problem in the normal way. Okay, and again, we'll go over that carefully as well. So let's jump right into it here. In the first problem, you can see that we have the bars by themselves. And in particular, notice that it looks just like problem or rule number 1 here. And since the bars are by themselves, and since it looks like this in particular, in other words, we have absolute value by itself on one side of the equal sign. with a number that is greater than or equal to 0. It has to be greater than or equal to 0. And the 6 down here is greater than or equal to 0. So it fits into these rules that we have to follow here. Since they do, it says that you are allowed to do the following. On the next step, let me zoom out here a little bit. On the next step, it says, follow me here, absolute value of x is equal to 6. X is equal to 6. X is equal to negative 6. All right, so the a and the 6 are the same thing there. Let's write that down. X is equal to 6 or x is equal to negative 6. Since we got x by itself, the problem's over. Okay? Since we got x by itself, the problem's over, and we have 2 answers. Okay, this won't be the last time that we have more than one answer to an equation, all right? But that happens sometimes. All right? But because x is by itself in both equations, you're done. If it wasn't, then you'd have to solve each problem, each equation here separately. We'll see that here in the next problem. Now, in the next problem, once again, you have the absolute value bars by themselves. Now, I know it doesn't look exactly like rule number 1 because in rule number 1, you just have a variable in there and that's it. But what the rule number 1 is really meant to imply is it's meant to imply just that you have the bars by themselves with nothing outside of it like a 3 or like a 7 or a plus 2, just the bars. It doesn't matter how big the inside part of the bars is, okay? You can still use this rule as long as there's nothing outside of the bars on that side of the equal sign, okay? And also the number on the other side of the equal sign has to be greater than or equal to 0, and it is, okay? The a and the 5 are the same thing here. Okay, so what do you do in that case? What you do is you take the inside of the bars, and whatever that is, it doesn't have to be x, but whatever the inside is, that goes here and here where it says x right there. So if it's absolute value of x plus 1, then you would write x plus 1 and x plus 1 in those 2 spots right there. Okay, so it doesn't have to be x, but these 3 things have to be the same. The x, and the x. So if it's x plus 1, then it's going to be x plus 1 again here and x plus 1 again here. Let's write that down. X plus 1 and x plus 1. And then what am I supposed to say? What are the a's here? Since a is 5 in this problem, we're going to say equal to 5 equal to negative 5. Like this. Okay? And what this creates now, you guys, it creates 2 brand new equations. They look like normal linear equations like we've been solving. All the way back in the very first section, okay, when we solved the linear equations, and we've seen other types as well. The one variable equations that you have to solve, all right, this is no different than that. Getting x by itself, just like that very first section, 1.4 that we did this semester, okay? So that means that there's no parentheses, there's no like terms to combine, but we do need to move the 1 over with the 5. Like this, and we end up getting 4 on that equation. Notice I'm doing the 2 equations separately here. Okay, don't try to combine them. Keep them separate and just solve them both separately. Okay, and then this one's negative 6. So the final answer here is two different answers again, 4 and negative 6. All right. Don't worry about that word or, by the way. If you forget to put that there, that word is not overly important right now. Just make sure to get the 2 answers and keep them separate. Don't try to combine it into one thing, okay? Just say x equal to 6, x equal to negative 6, x equal to 4, x equal to negative 6. Keep the 2 equations separate, but just circle them both after you get x by itself, okay? Next one here. And in the next 3 problems, like I mentioned a few minutes ago, the bars are not by themselves. So it is absolutely unacceptable to use any of these rules here until the bars are by themselves, because the bars are by themselves in all of these. Okay? So how do you get the bars by themselves? The easiest way to look at this is I want you to picture for a moment the bars. Just look at the bars. Right? Don't look at the 3. The 3 is separate from what I'm circling here. I know it's kind of hard to do that, kind of hard to see that. But the 3 is separate from the bars, all right? Just focus on the bars for just a moment. I'm going to pretend like that bar is, and use a different letter here, but I'm going to pretend like that's a variable, including the bars itself. So 3 times the bars equal to 12 is the same thing as saying 3 times x equal to 12. Okay, this is not, I didn't change the problem. This is a different thing here, but it's going to help us understand how to do this. Okay, how would you solve this problem? How would you get x by itself? Wouldn't you divide by 3? And you get x equal to 4? My point is this, okay? If you pretend like the bars are a variable and you get the variable by itself, okay, the way in which you get the bars by themselves, which is the first thing you always got to do in an absolute value problem, okay, the steps are going to be the same, all right? So just like I divided by 3 up here, and just like the 3's will cancel right here, the 3's are going to cancel right here as well, and just like the x is by itself, since the bars and the x variable are playing the same role right now, okay, that means that the bars now should be by themselves just like the x was. And it should be equal to the same number on the other side, 4. Because again, the bars and the x are playing the same role here. You should have a similar result. Okay, now that I've gotten that by itself, and we'll do a similar thing to that on problems D and E as well in case you're curious, but let's finish this up first. Just like I had over here where I had the bars by themselves, I now do what? I now use that rule up there. Follow me here. Absolute value by itself, y plus 5 is on the inside, and then I have a number that is greater than or equal to 0. It's 4, so all this applies here. Okay, the bars by themselves, number that's greater than or equal to 0. It has to be a constant number. You can't have a variable over here. Okay, but if you do, then let's go over here now. So y plus 5 was on the inside, so that means that y plus 5 goes here, and y plus 5 goes here. These 2 spots where the x's were now becomes y plus 5. Let's write that down. So I'm going to write down y plus 5 twice. And then what are they equal to? They're equal to a and negative a. But in this problem, the a is what? It is not 12, you guys. Remember, you don't apply this rule until you get the bars by themselves. And when you get the bars by themselves, it's no longer 12 anymore, is it? It's now 4. So it's going to be 4 or negative 4, like that. And now that you have the bars, now that you've gotten rid of the bars, rather, now you use the normal rules to solve for y, solve for the variable, get the variable by itself that you've done in the past, all the way back to the first day of class. Okay, get the variable by itself, but do the 2 equations separately. Okay, so I need to move over the 5 with the 4, don't I? And so we get what here? We get negative 1, and then the other one is negative 9. There we go. Okay. Let's keep going here. Again, if there's any mystery at all, and if you're sure that you know what the steps are, and you're absolutely sure, then that's fine. You don't have to do this. This is just something to help people visualize what the correct steps are. So I'm not going to use the same letter, though. I'll pretend like that those bars there are equal to variable y. Everything else is the same. The 7 is still there. Everything that's outside of the bars is still there. I'm just pretending like the bars are a variable. And then if I can get the variable by itself, I would then be able to get the bars by themselves using exactly the same steps. What steps would you use to get the y by itself here? Wouldn't you subtract the 2 over and then divide by the 7? Okay, something which we've done a number of times, right? So that's exactly what we're going to do here. I'll go ahead and write it down up here as well, just so you can see it. I'm kind of running out of space here. I'll put it up here. So if I move over the 2, I get this right here, right? And then if I divide out the 7, I get y equal to 2. Same, it should be the same result here, where the bars get by themselves, and it's going to be equal to 2 on the other side. Like that. Okay, and then you divide out the 7. Just like the 7's cancel up here, the 7's going to cancel here. And you get the bars by themselves, and just like the pretend problem that I wrote down up here, on the other side of the equal sign, you have a 2 as well. Now that the bars are by themselves, what do? That's always the step where we what? Where we always come up here. Where we always come up here and we say, okay, I have bars by themselves. Doesn't matter what's on the inside. The bars are by themselves. And I have a number that's greater than or equal to 0. It's 2 in this case on the other side of the equal sign. So let's follow it here. Absolute value of 3x. That means that 3x goes here without the bars. And 3x goes here. 3x and 3x. Let's write that down. And then also, let me zoom out a little bit more. There we go. And then the a and the negative a are going to be what? Well, since the a is equal to 2 this time, not 16, again, the a is not even figured out until you get the bars by itself. And so it's 2, not 16. So that 2 means that on the next step, it's going to be 2 and negative 2. Just like up here, a and negative a. And now that leads to what? That leads to 2 brand new equations, and we solve it in the normal way. Which means that we would divide out here, wouldn't we? Because you already have a single variable term on one side and a single constant term on the other side. So the 2 answers are going to be x is equal to 2/3 or x is equal to negative 2/3. And there you go. Okay. Let's try one more here before I have you guys try some. Okay, this will be the last one that involves rule number 1 at the top of the page. Well, at least it looks like it's going to, but something interesting is going to happen here. We'll go over that carefully, though. But once again, the bars are not by themselves, right? Bars are not by themselves. So what do we got to do? We got to pretend like the bars are a variable. I'll use the letter X this time since Y is in the problem. We don't want to confuse things by using the same letter when I draw up the pretend problem over here to the side. How do I get the X by itself? Subtract over the 8, right? In the same way, I'm going to subtract over the 8 right here, and I'm going to get that right there. Okay, but we have a problem here. Yes, it looks like the last few problems, right? You got the absolute value by itself. It is an equal sign. It definitely looks like somewhat the first rule, but there's a problem. It says that that constant number on the other side has to be greater than or equal to 0. It can't be negative, in other words. Okay, it can't be negative. It is negative in this problem, though, so what does that mean? Well, remember the very beginning here when I said that the absolute value has to always equal a positive number here? Has to always equal the positive number. Okay, the number on the inside, let me make this clear. A lot of people get this mixed up. It's okay for the number on the inside of the absolute value to be negative. It's just that the entire, when you figure out the absolute value of it, it's always positive. So if you have an absolute value bar by itself on one side of the equal sign, that means that the absolute value is equal to, it's got to be equal to something that's not negative, okay, because when the absolute value is by itself, then that is just the absolute value and nothing else. And so therefore it's got to be equal to something positive, or 0 at the least, but it can't be negative. And so that's where they bring this special case into play right here. Let me kind of make an arrow here so you can look at this later when you're studying. Okay, it says that if you have the absolute value bars by themselves, but the other side is a number that's less than 0, in other words, it's negative, then there's no solution. And that's exactly what we're going to write here. No solution. So no solution isn't just those problems where the variables disappear and you get a false statement and all that. No, no, no. It could happen here as well. But it makes sense because an absolute value, including the bars, again, not talking about just the inside only, but the whole thing, including the bars, cannot be equal to a negative number. Okay? And so there's no way you could have a solution here. So please go ahead and try problems 1 and 2. Don't do anything else because the other ones involve other rules that we haven't talked about quite yet. So just do 1 and 2 right now. Hit the play button. We'll take a look at those answers, and then we'll move on and take a look at the next rule. Okay, number 1. It's very similar to problem C up above. You need to get the bars by themselves. The 2 means that the outside 2 there means that the bars are not by themselves yet. This is similar to having 2 times a variable equal to 14. And so just like in problem C, we divide out. Okay, again, just like if you had 2 times, say, y equal to 14, you would divide by 2 there, wouldn't you? And so it makes sense that we would divide by 2 here as well. Here you would get y equal to 7. In the same way, you would get the bars equal to 7. And then once you get the bars by themselves, you what? You write down the inside of the bars twice, just like we've been doing. Okay, the 7 is positive, so you don't have to worry about it being no solution or anything like that. And then 7 becomes 7 and negative 7. Again, this is according to rule number 1 at the top because it looks like that. And now that the bars are gone, you just solve these 2 separate equations in their same normal way. Move over the 2's. You get this right here. Then divide out the 3's. And you get these 2 answers right here. And that is problem number 1. Problem number 2. Again, this is similar to if you had a variable plus 6 equal to 2. In that case, you would subtract the 6 over, wouldn't you? And that leads to this unique result right here where you got bars by themselves. But the problem, similar to problem E, the issue here is the fact that the other side is not a positive number, it's a negative number. Okay? And so don't try to do rule number 1 when the number on the other side of the bars is negative. Instead, we're going to say what? We're going to say no solution. Okay, so if the bars are by themselves, you have an equal sign, then there's 2 different things that could happen in that case. If it's positive, you do this. If it's negative, it's no solution. Okay, so that's basically rule number 1. Okay, but again, so important to get the bars by themselves first before you apply any rules. Let's now take a look at rule number 2. Get out a clean sheet of paper here again with the problems here. Problem F and problem G. And for that matter, problem 3 down here. All 3 of these problems here, what do they have in common? The bars are by themselves, but there's 2 different ones, but they're both by themselves on each side. Okay. When that happens, when they're both by themselves, one on each side, it is similar to rule number 2. Okay, you can see that all 3 problems are already like that, so you don't need to make any adjustments to make it look like this. It already is like that. But listen closely as far as how to write this out, because this is just when you have like an X and a Y. When the stuff inside the bars, though, is bigger than just an X or a Y, you got to be a little more careful about how you write it. Okay, the first part is not too bad, though. It's the second part we got to be careful of. Notice it says here, if you have X and Y, then it's still X and Y without the bars here. So what that basically means is that you take the insides of the bars, represented by X and Y in the rule, but in the actual problem, you take the insides of the bars, 4x minus 9 and 2x plus 1, and all you got to do is say that they're equal to each other. But that's just the first equation. There's going to be another one again here. And in the second one, this is where you got to be careful again. Notice it says in the second one, x is equal to negative y. Now, I want to interpret this here. This means negative 1 times y. That's what negative y always means. But we definitely want to think of it that way here because the y is more than one term. Okay? And so it's negative 1 times 2x plus 1. But I'm doing something wrong here that I want you to realize, and then I'll fix it, okay? Oh, I'm sorry. I forgot to write down the 4x minus 9. Excuse me. So write that down first. 4x minus 9. So in other words, the first part, when you got these double absolute value problems here, the first part is the same on both of them. 4x minus 9, 4x minus 9. But it's the 2x plus 1 on the second part. In other words, it's the thing inside the second absolute value. When you bring it over to the second part, it's negative 1 times 2x plus 1. But there's an issue here. Okay, you have to put a bracket around this because it's got more than one term. I'm sure I've said it before, but let me say it again. Whenever you have something with more than one term in it, and you have to multiply the whole thing by anything other than positive 1, and that would include negative 1, you got to bracket it. Anytime you have something that has more than one term in it, you're supposed to multiply the whole thing by something else other than 1, you got to bracket it. Okay, and so this is one of those situations. So in all three of these problems here that we're going to be working on here, you guys, this one as well, you're going to have negative 1 times 6 minus x on the second part. You're going to have negative 1 times 3x plus 9 on the second part. And you're going to have to put a bracket around the 6 minus x and around the 3x plus 9. Okay. Other than that, it's pretty much the stuff just stays the same. That's what the rule is saying, though. It just doesn't have a bracket up at the top of the page where it says negative y because it's just y. If you multiply by a single term, you don't need a bracket around the single term. It's when you multiply negative 1 times something that has more than one term in it, that's different. Then you need to put a bracket around the thing that's being multiplied by negative 1. Anyway, let's solve these equations now. The bars are now gone, so just like before, you just have to solve them in the normal way. Just keep the two equations separate when you solve them. So I'm going to go ahead and move the 1 over with the negative 9. That would be negative 10. I subtracted it over. I'm going to subtract over the 4x with the 2x. That's going to make it negative 2x. Okay, and then I'll divide out. And I get x is equal to 5. Here you got to distribute first, right? That's what we do in the linear equations that we've been doing so far this semester, the one variable linear equations that we've done so many times. Then I'll do the same thing as I did in the last problem. I will move over the 4x. So negative 2x minus 4x is going to be negative 6x. If you add the 2 over with the 9, though, you're going to get... Oh, I'm sorry. I mean, I knew there was a problem. I knew something was going wrong there. I apologize. This is minus 1. Negative 1 times 1 on the second part of the distribution there is equal to negative 1, not negative 2. So when I move over the 1, negative 9 plus 1 is negative 8. There we go. Now things are correct. Now I divide out and I get x is equal to, when you put this in lowest terms, 8/6 becomes 4/3. Negative divided by negative is positive. Okay, and so it's positive. It's a positive fraction. Let's do that one more time here. Okay. So again, the first part and the second part stay the same on the first of the two equations that you do. Okay. But then on the other equation, again, the first part stays the same, but it's the second part of the second equation that you got to be careful of. You got to say what? You got to say negative 1 times, and then the second part, 6 minus x. Just like I did negative 1 times the second part here, 2x plus 1. That removes the bars. And now we just have to do the normal thing to solve. So I'm going to move, I'm going to add the x over with this x. I'm going to add the 3 over with the 6. Since the 3 was negative, I add it over. I then divide out and I get x equal to 9/2. But then something funny happens on this other one. Don't panic if you are wondering what goes on there. If I distribute this out, I get this right here. Distribute out the -1. But then when I, since this is plus x, I got to subtract it over. But if I subtract it over, what happens? I get one of those equations where the variables disappear and it's a false statement. So that means what? That means there's no solution. But that does not mean, and this is what I'm concerned about, make sure you understand this, that does not mean the whole problem is no solution. Because when we do these two separate equations, you guys, they are independent of each other. So that means that if one of them gives you no solution, that doesn't mean that the other one doesn't count, okay? It still counts because they're independent of each other. So since this one is no solution, that just means that this one doesn't produce an answer right here, this equation. But this equation, since it's independent of the other equation, it still counts. And so you get an answer right there, 9/2. So in one of these problems here, where it produces the two equations, if one of them gives you no solution, please remember the other one still counts if it gave you an answer. Okay? So it's a little bit different than when we did the systems of equations and just the single equations, not the two separate independent equations, but the single equations on the first day of class. Okay? In those cases, when you got a result like this, the whole problem was no solution, but not here. Okay, please try number 3 right now. Okay, again, it's similar setup. Let's see how you do on that, and then we'll flip the worksheet over to the second page after that. All right, number 3. Again, we have the double absolute value bars here, one on each side, each one of them by themselves, isolated. And so what do? The first one is just everything stays the same. Second one, the first part stays the same, but then as we mentioned, the second part of the second equation, you go -1 times, and then you use a bracket if there's more than one term inside the bars there. And there is 3x plus 9, and so we put the -1 in front of the bar, or I'm sorry, in front of the parentheses there. Okay, we solve these resulting equations using the normal methods. And we end up with x equal to 3. Okay, distributing here and doing all the normal stuff, dividing out by 9 eventually, we get x equal to -1. So 3 and -1. So that is how to use rule number 2. You'll see at the top of the page, though, that rule number 3 and 4 involve, as I go back to my clean sheet of paper here again, rules 3A actually says 3A and 4A, by the way. 3A and 4, the A is actually not meant to be there. It should be just 3 and 4, okay? There is no 3B and 4B, okay? But it's basically 3 and 4. Think of it that way, okay? But you'll notice that they're inequalities now. They're not equal signs anymore. But again, in both cases, the number on the other side is got to be positive. If it's not, we have some special rules for that we'll get to. They're rare, but rarely do they need to be used, but we'll talk about that. But for now, let's look at what happens when those are positive constant numbers on the other side of the inequality symbol of the alligator mouth with the absolute value by itself on the other side. So this is what our next step is going to look like in each one of these two cases right here. And then if x is not already by itself, we'll get it by itself. Kind of similar process to when you have equations, okay, with the equal sign. However, though, if you look at the back side or the second page of our current section here, it says write the solution set in interval notation. That should look familiar to you from section 4.1 when we wrote the solution set in interval notation in that section, and in 4.2 somewhat as well. We first of all did what? We first of all did the number lines, right, to make it easier for us to see what the interval notation is. And so what I want to do right now is I want to show you how to, and let me tie this all together here, how to get from these two steps right here, whether it's this problem or this problem, once you're on one of these steps here, how do you get from that to the number line? Let's talk about that. I'll put it right above it here, and I'll give you an opportunity to write this down, all right, as I talk about it. Go ahead and start writing that down. But you can even pause the video if you're concerned you're going to miss something that I say. But I've got it on the screen here, so you can pause it if you want, or just write it down as I talk. But in the first one, or pardon me, I've got a little bit out of order here, but let's talk about 3a here first. It says that if the absolute value, let me move that over, sorry. There we go. Now we can see it all together. Rule 3a right here says that if the absolute value is by itself and it's less than, key thing there is less than, whereas rule number 4 is greater than. Totally big difference there, so make sure you understand that. Less than and greater than, two different things. But if the absolute value bars are by themselves less than a positive number, then you write this on the next step, and I'll show you how to do that. But then once you do that, okay, you should have something in the middle here with a variable, and it won't always be x only. Sometimes you'll need to get the x by itself, and I'll show you how to do that too. But eventually, you guys, the x will be by itself. And so eventually the x, we're going to get the x by itself if it's not already by itself. And if you do it correctly, the smaller number should be over here, well, actually it doesn't always have to be over there, but what's important is the alligator has to be eating the variable if the smaller number's on the other side of it, okay? And whereas over here, see how there's two alligators here. So this alligator, if he's next to the smaller number, he's got to be eating the variable. But if this alligator's next to the bigger number, he's got to be eating the bigger number instead of the variable, okay? In other words, it could be switched around where the bigger number is over here, but as long as the alligator's eating the bigger number, but not the smaller number, okay? Because again, there's going to be two different alligator mouths here, all right? One of them will be eating the bigger number. The other one will be eating the variable, okay, with the smaller number on the other side of the one that's eating the variable, all right? So if you do it correctly, it's going to look like that. And when that happens, okay, you're always going to shade in the middle. All right. In other words, you're going to take those two numbers, a smaller number and a bigger number, you're going to bring them down, doesn't matter what they are, and but you got to wait till you get x by itself before you do this. So the numbers are going to change along the way, but when x is by itself, you take those two numbers, you bring them down, and then you just shade in the middle. Then you figure out your brackets the same way we did before. We'll review that again. And then you can do the interval notation after you're done with your number line. When it's rule number 4, and again, the big difference is that that's when the absolute value is greater than. In other words, the absolute value is getting eaten by the alligator, whereas down here it's not. Okay, when absolute value is getting eaten by the alligator, okay, then you got to say what down here? Let's start out with rule number 4 in the top of the worksheet. It says that you take the inside of the bars and you say greater than positive A, less than negative A. Again, greater than positive A, less than negative A. A lot of people get this wrong, okay? Don't let that be you. A lot of people say greater than. They say greater than twice. That's not right. It's greater than positive, less than negative, okay? Whereas up here, it's the opposite. It's less than the positive. The x is in the middle, and the x is less than the positive, but the x is greater than the negative. Okay? And so, please notice the difference there. Okay? Greater than positive, less than negative when it's this problem here. Okay? Where the absolute value is greater than. Less than positive, greater than, talking about the x in the middle, less than positive, x is less than positive, x is greater than the negative, okay? Because the alligator's eating the x in relation to the negative here, all right? It would rather eat the x than the negative number here. And so x is greater than the negative, but it's less than the positive, okay? So when you get rule number 4, though, where it's like this right here, where the absolute value is greater than, okay, Eventually, you'll get x by itself if it's not already, okay? And if you do it correctly, again, the bigger number, or the x will be greater than the bigger number, and the x will be less than the smaller number, okay? I know that seems like a contradiction. How can you be greater than a bigger number and less than the smaller number at the same time? Well, it's just different parts of the solution. Remember, when you do an inequality, there's a whole bunch of solutions. Okay, the solutions are the ones that are greater than the bigger number, and they're also the ones that are less than the smaller number. It's just both of those different sets of numbers there that are. So they don't have to both be. X does not have to be greater than the bigger number and less than the smaller number at the same time. Okay, it's just that it's those numbers that all work, okay, for that particular inequality. So when it's like this, you guys, and again, if you do it correctly, it should come out like this, you will always shade the first and the last interval, but not the middle one. Exactly the opposite of rule number 3. Okay, and so you just bring down your two numbers down here, smaller and bigger. You shade them. You figure out your brackets. You can see I put round brackets right here because the alligator doesn't have feet. But if the alligator did have feet, we would use a square bracket before we do the interval notation, just like we did in the last 2 sections. Okay, so let's go ahead and try this right now. Okay. If you're still trying to get used to it, don't worry. We're going to keep on talking about these things as we go through each problem. All right. So let me go ahead and pull out the first problem here. You can see that in the first problem, it already looks like rule number 3 already, where the 5 is on the other side. So let's go ahead and write that. Yeah, actually, we don't need to zoom out. We're good. So on the next step here, it says what? It says absolute value of x less than 5. The 5 is positive, so that's fine. And then we get what? The x is in the middle. Let's write that down. And then it says what here? It says negative 5 over here on the left. And then it says positive 5 over here on the right. And then your alligator should be eating the variable instead of the smaller number. The negative 5 is a smaller number. And then when it comes to the bigger number, the alligator is going to be eating the bigger number. Okay, so the alligator wants to eat the bigger number, but not the smaller number. That's what it comes down to. Okay, he wants to eat the bigger number and not the x. But when it comes to the smaller number, he'd rather have the x. Okay. And so when that happens, what it's basically saying, it's saying that in order to be a solution, it has to be the x's have to, in other words, whatever number you plug in here, it has to be less than 5 and greater than negative 5 at the same time. So what I'm going to do is I'm going to put those two numbers down here, okay? And whenever it's written in this 3-part thing right here with the x in the middle and the 2 other parts sandwiched around it, as long as it's in that order, like I said, where the alligator's eating the bigger number but not the smaller number, then you always what? Well, according to that thing I just showed you right here, when that happens, when it's written like that, there's the 5 right there, there's the negative 5 right there, you're going to always shade in the middle. So let's do that right now. There we go. And that's where your solutions are. Not on the sides on this one, just in the middle. What kind of, remember, we always have to put brackets if you have any numbers on the number line that are shaded on just one side of the number. Well, that's the case with both of these. Both of these are shaded on only one side of the number itself here. Okay, so I need to close this thing up with round brackets because neither negative 5 nor 5 has an alligator foot next to it. It's just the alligator mouth. All right, as we talked about in the last couple of sections, that's how it works with the alligator feet. Now that I have my shading and my brackets, I now what? I now do the interval notation, and it is going to be negative 5 comma 5, like that. I just follow the number line when I do the interval notation, and that's the same thing we always do, right? That's why it's good to do the number line first. So you can figure that out. Next. Same idea on the next one here. We have an absolute value that is less than, key thing there is that the absolute value is less than a positive constant number on the other side. Then what we do is we take the inside of the absolute value, no matter how big it is, just like when the absolute values were by themselves before in rule number 1, okay, you immediately go down to the step to where the absolute values disappear. It's the same thing here. If you have 3x plus 5 inside of here, let me show that all together at once. There we go. If you have 3x plus 5 inside of there, the 3x plus 5 now goes there in the middle. Okay. That x there in rule number 3 represents anything that's inside there. It doesn't have to always be x. And so the 3x plus 5, whatever's in there now goes in the middle. And then you do the inequalities like this right here, where the positive 17 is getting eaten by the alligator, but the smaller number, negative 17, is not. Okay, again, alligator wants to eat the bigger one, but does not want to eat the smaller one. That's how it goes. But we still need to get x by itself. How do we do that when there's 3 parts like this? We haven't seen that before. Here's the best way to approach it. Pretend like if you're having trouble visualizing this because there's 3 parts, you're used to just having 2 sides, pretend like you're just looking at these 2 things. Just pretend like the negative 17 is not there for just a minute, okay? So now you only have 2 parts. How would you get x by itself? Well, this is just like a problem we had in 4.1. You move over the 5, you add the 5, or pardon me, you subtract the 5 over. And that would give me that right there, right? And then you would divide by 3, wouldn't you? Okay. Well, my point is that, let me move this a little bit more in the middle here. My point is that whatever steps you do to these 2 parts right here, you do that same thing to this 3rd part over here. So since I subtracted 5 from these 2 parts, the 5's cancel here, and then you get 17 minus 5 here. I'm also going to subtract 5 from the negative 17 as well. And that gives me negative 22. And then just like I would divide by 3 if these were the only 2 parts that we had, ignoring the negative 22, it would also make sense then that we would also divide by negative 22. So in other words, whatever you do to these 2 parts right here, do that to the 3rd part also, and you'll be fine. Okay? You'll be fine. What do we get? Well, if I put the fractions in lowest terms like normal, I get the 4 there, and I get this negative fraction over here, which is already in lowest terms. But notice what's going on here. Just like in the last problem. X is by itself. All right. The alligator wants to eat the bigger number, but it doesn't want to eat the smaller number. Okay. And so when the alligator is less than the bigger number and greater than the smaller number, again, we shade in the middle. Okay? And that's exactly what this says here. So you take those 2 numbers, you bring it down, always put the smaller number on the left, like we've said in the past. So there we go right there. Shade it in the middle. There we go. And once again, the alligators do not have feet. So we use a round bracket on both of these. And now that I've done my shading and my brackets, I'm ready to do my interval notation. Very similar looking to the last problem. There's your interval notation right there. Okay. All right. And that's problem I. Okay, moving on to problem J. You may have noticed if you kind of saw it as I was doing the last problem that I had the wrong problem J on the worksheet that I had on the screen. The one that you should have on your worksheet that I sent you as part of your worksheet packet is this one right here. So this is the one that we're going to do. Okay, I accidentally pulled out the wrong sheet right there with the wrong problem. And all the other problems are correct, though. It was just this one that was off. So I got a new sheet here just to do this problem. So now everything that we're doing on this video is the problems that you have in your worksheet packet. Don't worry. But what I do want to point out here is that now the absolute value is greater than or equal to, same idea. Whether it's got alligator feet or not, it's when it's greater than that you use rule number 4, okay? Rule number 4 right here, where instead of the alligator wanting to eat the bigger number and not the smaller number, it actually is going to do the opposite, okay? It doesn't want to eat the bigger one, but it does want to eat the smaller one. It does the opposite thing, okay, from what rule number 3 does. And so that's why the shadings are in a completely different place. Instead of being in the middle, it's on the ends. I'll show that to you again here once we get to it. But let's get the absolute value bars, let's get the rule set up here. Since the bars are by themselves, you are allowed to use the rule right now. Like always, since the bars are by themselves, you can now use this rule. Since it's greater than and greater than or equal to also applies to that. Just like if this had said less than or equal to up here in rule number 3, you can use rule number 3 for that as well, whether it has alligator feet or not. The rule is basically the same. Okay, it's just that the only thing is that if it does have alligator feet, you got to have alligator feet over here as well. And I mentioned that right here, where if it's got alligator feet, it's the same idea. So if there's alligator feet next to the absolute value bars over here, then put the feet on both of these here. Okay, both of them here in these alligators and both of the alligators here. All right, and so we'll do that. Okay, but other than that, the rules are exactly the same, whether you have alligator feet or you don't have alligator feet. Okay, now, so rule number 4 is saying this. It's saying that the inside of the bars, you write them down twice. Just like, see here, I had the X, and then I wrote that down twice there. Okay, since, and let me zoom out so you can see it. There we go. That's a little bit too much. There we go. So see how the X there got written down twice? Whatever's inside the bars is the same thing. So 3x minus 3 here means 3x minus 3 here, and 3x minus 3 right there. So I did that. And then again, notice what it says. It says greater than or equal to A, which is greater than or equal to 9. And then it says less than or equal to negative 9. Okay, so greater than positive, less than negative. All right? Greater than the bigger number, less than the smaller number. The opposite of rule number 3. Now that I've gotten rid of the bars, I do my normal thing to get X by itself. Subtract the 3, or pardon me, add the 3 over on both of these. Okay. If I add here, I get negative 6. If you divide by a positive 3, the inequality does not flip. It's when you divide by negative that it does that. And we get X is greater than or equal to 4, or what? X is less than or equal to negative 2. All right, now, as I promised you guys, when you get the X by itself, and this should work, okay, if rule number 4 is what you're doing, this should always happen. When you get the X by itself, the alligator should be eating the X when it's next to the bigger number, and it should be eating the smaller number when it's next to the smaller number, not the X there, okay? So greater than the bigger number, less than the smaller number. When that happens, and that does happen here, you can see that. Greater than the 4 is bigger than negative 2. So it's greater than, the X is greater than the bigger number. It's less than the smaller number, with the alligator feet in there as well. But the alligators are going the same direction as it is in rule 4 here. Okay? And when that happens, you put your 2 numbers down here and you shade the first and third interval, not the middle one this time. Let's do that. So put down 4 and negative 2. Smaller number always goes on the left. And then we shade the first and the last interval, but not the middle one. Okay. Okay, that's rule number 4. Okay, so when you have absolute value greater than, it's always the first and last interval. Eventually, after you get x by itself and everything, don't put 9 and negative 9 on the number line, though. Remember, you got to get the x's by itself first, and that makes it different numbers right there, 4 and negative 2. And then, like I said, when the absolute value is less than, okay, that's when you what? That's when you do the middle of that's when you shade the middle after you get the x by itself and you figure out the numbers. Okay? All right, so let's wrap this problem up here. Because the 4 and the negative 2 have an alligator foot next to them, these are going to be square brackets this time instead of round ones, like that. And now that I'm done with my shading and my brackets, I do my interval notation. As we learned in the last section, whenever you go from left to right and the shading stops but then starts back up again later, what do? We go like this right here. And then you can either put the word or in between or the letter U, either one. Like I said, I'll do U this time because that's what the book likes to do in chapter 4. And then it starts back up at 4 and it goes all the way to forever to the right, and that means infinity. Infinity and negative infinity are always round. Negative 2 and 4 are square because the number line tells us that it is. Okay? All right. Problem K is very similar to that, all right, where you can't see it yet because we don't have the absolute value by itself, but let's get it by itself first, and then we'll talk about it. Because theoretically, you guys, as I've mentioned many times in this section, you don't even want to think about the rules until you've got the absolute value bar by itself. You don't even want to think about them, okay, because you don't want to apply them too soon. You've got to wait until the bars are by themselves. So let's do that. Same thing we did on some of those problems on the front when we were doing equations. If the bars are not by themselves, you guys, you get them by themselves by pretending that the bars are a variable. Like, for example, let's pretend like that red thing I just circled there, which is the bars. Let's pretend like that is a variable y. Okay? And so that would make the problem look like this right here. How would I get y by itself if that's what I was doing here? Okay, wouldn't I subtract the 2 over and then divide by positive 3, which again would not flip the inequality because you divided by a positive? Okay. Isn't that what you would do, though? You would subtract the 2 and then divide by 3. So you do exactly the same thing here. Same steps as they would be if it was a variable, as we mentioned on the problems on the front. It's the same approach here. Okay, so let me do that. I'm subtracting the 2 over, and then I'm dividing out the 3, and then I'm getting what here? The 3's cancel, just like the 3's would cancel if I divided by 3 here after moving over the 2. Same idea. And I would get this right here in the real problem. That's what it would look like. Okay? Okay, now notice though, after I get the bars by themselves, don't think about it before that, as I mentioned. Okay? The rules are what? Says that again, if the bars are greater than a positive number on the other side, which is what we have here, the bars are by themselves greater than a positive number, that means that I what? That means that just like in the last problem, I write down the inside of the bars twice, like that, and then I say greater than the positive, less than the negative. No alligator feet this time. Greater than the positive, less than the negative, when the bars are greater than. Okay. And now that we've gotten rid of the bars, we now solve these inequalities like normal. I add the 1 over to the other side. It would look like that. And then on this side, it would look like this. I then divide out the 2. And I get what? I get x is greater than 3/2. And also x is less than -1/2. Okay. So again, you can see that x is greater than the bigger number. 3/2 is bigger than this negative fraction over here. Okay. Because the fraction is positive and this fraction is negative. So we have x is greater than the bigger fraction. X is less than the smaller fraction. Okay, fits right into what it should have been, all right, because rule number 4 is always like that. Always greater than the bigger and less than the smaller. So we put those two numbers on here, like that. And what is the shading in rule number 4? It's always the first and the last, isn't it? Not the middle, though. Okay. Rule number 3 is the middle. Rule number 4 is the first and the last. This time I use round brackets because the alligator does not have feet next to either of those fractions. Okay, and so those fractions should have round brackets. And now I'm ready for the interval notation. Interval notation says negative infinity all the way up to -1/2. Close up that bracket there as the problem tells us to do. Then because it stops and starts back up again, we put the U right there. Then we go back, or we start back up again at 3/2. And we go all the way to infinity, don't we? Like that. Okay? And there you go. So that is rules 3 and 4. You can see here in problems 4, 5, and 6. And number 4, it's going to be rule number 4, isn't it? Because the absolute value is by itself greater than. Rule number 5, the absolute value is by itself and it's less than. So that's rule number 3. And then rule number 6, we're not 100% sure until we move over the 4. But yes, as you'll see here, and you could probably guess this already, once you get the bars by themselves after moving over the 4, it will be less than as well. So that would also be rule number 3. Okay, so please try 4, 5, and 6. Do not do those last two problems, L and M, okay, because you can see there's negative numbers on the other side of where the absolute value bars are located, and so that's a whole different thing. Okay, just like those problems we saw in the front that were different. We'll talk about that at the end. But do 4, 5, and 6 first. We'll see how that comes out after you hit the play button, and then we'll do those last two problems. Number 4. As you can see, it's rule number 4 because the absolute value is greater than. And so let's get started with that. Since it's rule number 4, we write down the inside of the absolute value bars twice. Okay, in these two spots. And rule number 4 says to do greater than the bigger, less than the smaller. Now that we've gotten rid of the absolute value bars, we then solve those inequalities, doing the normal steps right here. And we end up with those two numbers right there, x greater than 5, x less than 1/3. So again, we have greater than the bigger number because 5 is bigger than 1/3. Greater than the bigger, less than the smaller. Okay. When that happens, we always, after we put those two numbers on the number line, we always shade in the first and the last intervals. Then we do our interval notation after we put the round brackets on the number line because the alligator doesn't have feet. And there's your interval notation right there. Number 4. Number 5, on the other hand, and it's the alligator that makes all the difference when you have the absolute value. Okay, when the absolute value is not getting eaten by the alligator, but the alligator wants to eat the other number or the number on the other side instead, then we do what? Then we put the thing inside the and make sure that the absolute value is by itself first, by the way, as always. But we put that in the middle, rule number 3 in this case, when it's less than here and the absolute value is by itself. Rule number 3, and then we put... we set it up so that the bigger number's over here, so that the alligator wants to eat the bigger number, but it wants to, the smaller number, -5, is over here, and the alligator doesn't want to eat the smaller number. So rule number 3 again, it wants to eat the bigger number, but not the smaller. But rule number 4 actually does the opposite thing of what we would expect. Again, it doesn't want to eat the bigger number, but it does want to eat the smaller one. Okay. That's just how it works, okay? Then we need to get the x by itself. We did that same thing in problems H and I right above this here, where since it's x plus 1, we need to move the 1 over, okay? And if you imagine just doing these two parts right here, okay, you would just subtract the 1 over with the 5, right? But remember, whatever you do to those two parts, you got to do it to this part also. And so that gives me this right here, subtracting 1 from all 3 parts. And since the x is less than the bigger number, 4 is bigger than -6. X is less than the bigger number, greater than the smaller number. That means that whenever that happens with this 3-part inequality, as we call it, the 3 parts, that's when you shade the middle, you guys. That's when the middle is shaded, all right? The alligator's got feet on both of these, and so I use square brackets on both of those. And then there's my interval notation based off the number line. Okay. One more problem here where this time we need to get the absolute value by itself. Okay, number 6. We need to, again, imagine that the bars are a variable. If that had said y plus 4 less than or equal to 5, wouldn't you subtract the 4 over? And so you do the same thing here, okay? When you have the bars plus 4, it's just like having y plus 4. You subtract the 4 over, okay? And you get this right here. Once you get the bars by themselves, what do? Well, it depends. If it says the bars are less than or equal to, same thing, 1 or any positive constant over here, then that's, again, where you do the 3-part inequality, where you put the inside of the bars in the middle, and then you put the bigger number over here, the smaller number over here, so that the alligator wants to eat the bigger but not the smaller. Okay. In other words, you put the alligator mouse going in that same direction there that I've got there. We've done that on all of these. You then subtracted, that's why there's a slash mark through there. I subtracted the 2. Pardon me, I added the 2 since it's already -2. I added 2 to all 3 parts. That's what makes the 2 cancel. Now I can cancel it out. And I get x by itself in the middle with 1 and 3 now on each side. And when it's written like that, like we said before, that means you put the 1 and the 3 on the number line and you shade the middle. Less than the bigger, greater than the smaller in the 3-part format. That's when you shade the middle, just like that thing I showed you earlier, okay, right here. Okay, right there in the middle. It's just like this right here with the 3 parts, smaller, x, bigger. Okay. I used square brackets because the alligator has feet on both of those. And then I did my interval notation. So that is how to do rules number 3 and 4. Okay. Problems L and M. I'm just going to do these real quick here. I've already got them written down. Why do the answers come out like this right here? Remember, it all comes down to this, and it mentions this in the special cases on the front right here. But instead of just memorizing these only, let's understand why they are no solution in all real numbers here. Okay, it all has to do with the fact that an absolute value can never be negative, right? It always has to be positive or zero at the very least. And so here's the thing, you guys. This thing right here, because it's an absolute value, and it's only an absolute value, there's nothing else there on that side of the inequality symbol, it cannot be less than zero, can it? If something cannot be less than zero, isn't it impossible that it would be less than -2? What are the numbers that are less than -2, you guys? -3, -4, -5, -6, and so on, right? Absolute values can never be -3, -4, -5, -6. Okay, those numbers are too small. All right, those are negative numbers. All right, if a number and an absolute value is a number, we don't know what it is yet. It depends on what the x is. But the point is that no matter what the x is, no matter what x value you plug into this thing, the absolute value can never be less than -2 because it can never be negative to begin with. You can't be less than a negative number, okay, if you're not negative to begin with. Remember, something that's less than a negative, as I just mentioned, has got to be even more negative. -3, -4, -5, -6, for example. Okay, so if you have an absolute value by itself and it's less than a negative constant number, that's no solution, meaning that there's no possible number you could plug into x that would make this statement true right here. No possible way. On the other hand, though, if you have an absolute value by itself, which again means that it cannot be negative, and it says that it's greater than or equal to also counts, but if it's greater than a negative number, that's always going to happen no matter what. Because remember, this can never be negative. It's always going to be a positive number or maybe zero at the least. Positive numbers and zero, those numbers are never, ever going to fail to be greater than -12. They always will be greater than -12. They will always be greater than any negative number in the world, including -12. So no matter what number you plug into x, this absolute value right here that I circled will always be greater than or equal to -12. You could put any negative number here and it would still be all real numbers because it will always be greater than or equal to any negative number when it's an absolute value. Absolutely. Okay, so when you have an absolute value bar by itself and a negative number on the other side as opposed to a positive constant number, you instead have a negative constant number like -2 or -12, or like we saw right here in problem E, -7, when it was absolute value by itself equal to a negative constant number. In those cases, all right, you don't need to do all this other work that we've been doing on the other problems. It's either going to be no solution or all real numbers, depending on which one of these three you're talking about. It's when it's greater than a negative that it's going to be all real numbers, because a positive number is always greater than a negative, and that's what absolute values are, right? Positive numbers are zero. Okay. The other two, though, will be no solution, like we said. Okay, so this concludes 4.3. Lots of talk about absolute values. Let me know if you have any questions. Make sure to be really careful also to not get your rules mixed up. There's 4 of them in this section, so we want to really be careful there. But yeah, let me know if you have any questions. Okay, you have a good day, and I'll see you back for section 4.4.